Now we're on to chapter 8, talking about stoichiometry. So, when we are dealing with the numbers, dealing with balanced chemical equations, and then the terms between them, this is called reaction stoichiometry. It's sort of like chemical accounting. So, it's when we deal with the amounts of reactants and products and these types of things and how they're interchangeable. So, students usually have a hard time with this, especially the dimensions when it comes to getting the information from balanced chemical equations. So that's a step that students typically have a really hard time with this. And let's do an example, a colloquial example, before we talk about chemical reactions. So making pancakes. So we have our reactants and we have our products. We have 1 cup of flour, 2 eggs, a half a teaspoon of baking powder. You mix them together, you fry them on the pan, you get 5 pancakes. So now we have a 1 to 2 to 1/2 to 5 ratio. I mean, I know it's sorry that we're using a fraction of something here, but I'm trying to make it as simple as you can with a recipe. And now it tells us certain ratios, like there are 2 eggs to 5 pancakes, for instance. So this is going to become important when we talk about chemical reactions. And we can also do other things. So let's say we have 8 eggs and we use these 5 pancakes or 2 eggs. So that means 8 eggs can make 20 pancakes. So now we can use ratios that we learned from chemical equations and outside information to say how much products we can have. So these types of ratios. So let's do a chemical reaction here. So this is this ammonia synthesis from hydrogen. So 3 moles of hydrogen plus a mole of nitrogen makes 2 moles of ammonia. And notice I'm even using the words moles, and I said the molar ratio. That's what we do in chemistry, okay? So when I want you to start thinking, when you look at a chemical reaction, the first thing you're going to think is moles, moles, I see moles. So think of this as units or moles. You can use it as molecules, but typically what we try to train you young chemists to do is to look at moles. And now, similar to the pancake example, we can then look at molar ratios of things. So using the balanced chemical equation, for instance, there's a 2 to 1 molar ratio between ammonia and nitrogen. And that is because there's a 2 in front of ammonia and there's a nothing, or assumed a unity in front of nitrogen. And you can even drop that 1 in front of mole nitrogen if you want. When I write it, I typically do. So from these, we can get, from balanced chemical equations, we can get ratios. And not only that, from the previous chapters, we know that we can convert between mass and moles. So when we start with massive products, we can convert to massive reactants convert to moles of reactants, then can, from a balanced chemical equation, can be, I just said products, but I guess it doesn't necessarily have to be products. You can go to another species and then get the mass at species. So this is something that you can do from the chemical equations. And this middle step, the yellow box, the moles of A to moles of B, this is where students have the hardest time. This is the new concept for this right now. And it is one of the more difficult steps that students have. So let's do this. Combustion of octane here. The balanced chemical equation gives us the ratio of 2 moles octane to 16 moles carbon dioxide. Using this relationship, how much carbon dioxide will emitted per 500 grams of octane. So 5 times 10 to the 2 grams, that's 500 grams of octane. So we're going to burn 500 grams of octane. How much mass of carbon dioxide are we going to have? So I was looking for mass of carbon dioxide. We're going to end up with grams carbon dioxide. So the idea is we'll start with mass of octane, get the moles of octanes, convert to moles of carbon dioxide, and then finally get mass of carbon dioxide. You can see it's already written there in the bottom for you. So starting with 500 grams of octane and a mole of octane, you can calculate this out as 114.3 grams of octane. You do this by 8 times the atomic mass of carbon plus 18 times the atomic mass of hydrogen, and then the molar ratio. I honestly, when I do this, I would just go ahead and drop it down to 8 to 1. but if you want to do the 16 to 2, that's fine too. And then you can see the units cancel, and then the molecular weight of carbon dioxide, and we're left with 1,500 grams of carbon dioxide is the answer. So you can see it goes there like that. So, and again, the step that students usually have a hard time with is the ratio between carbon dioxide and octane. So this is the one that students find the most confusing. But you get that from the balanced chemical equation. So now let's go on and talk about limiting reagents, theoretical yield, and percent yield. So we have, remember the pancake reaction property or equation? So let's say that we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes can we make? So the idea is that we're limited by something. So we need to look and see which one of these are we limited by. And using the balanced chemical equation, 3 cups of flour limits us up to a maximum of 15 pancakes. 10 eggs, using the chemical equation, the ratio, we can form 25 pancakes. And the 4 teaspoons of baking powder, baking powder can make 40 pancakes. So we have to look at these, and which one do we pick? We pick 15. We pick the lowest one. So that means that the eggs and the baking powder are in excess. So we are limited by one reagent, and the rest we have excess. So in order to form 25 pancakes, we need more flour. In order to form 40 pancakes, we need more eggs and we need more flour. So we are limited by one of these reagents, and in this case, it's the amount of flour that we have. So things go until you're limited by something typically. So as mentioned before, flour is a limiting reagent, and we see this in many other things. Algae, for instance, grows typically until it's limited by a nutrient. And when there's a new nutrient, you get an influx of algal growth. Either if it's human caused, it's a eutrophication, but we see some natural forms of this throughout the oceans, for instance. So let's say we cook all our pancakes, and then we have enough flour, 15 pancakes, but something happens. We burn some, one falls on the floor, I don't know. Either way, we didn't get all our 15 pancakes. We only got 11 pancakes. So this would then be our actual yield. So due to issues that came up for whatever things, we would only get a certain amount of yield, and then we get our percent yield. It's the actual yield divided by the theoretical yield times 100%. So we would actually, we were expecting 15, but only get 11. And in doing so, we get our percent yield of 73%. So we made 73%. And this makes sense. I mean, if you're baking something and you are the plant manager that's making something, I don't know, Twinkies, and you have enough materials and you make sure that you have enough that it's relatively close. You don't have too much excess, but you certainly have the limiting ones where they're either perishable or more expensive. And then you think you're going to make 10,000 Twinkies, you only make 9,000. So your limiting reagent, then your limiting reactant, or sorry, your actual yield is 90% kind of thing. Sorry, I keep on using these terms back and forth. So this makes sense in a sort of a colloquial sense. So, but we see this also in chemistry and chemical reactions. So the limiting reactant or limiting reagent, I usually say limiting reagent. I don't know if the limiting reactant is a new way of saying it. Guess I'm getting old if they're changing the terminology of chemistry. It means I'm really old. Jeez. So limiting reagent is the one that is limiting the amount of product. And theoretical yield, this is how much, assuming everything goes perfectly, this is how much you should get. Your actual yield is something that you measure. So this is something you determine by experimental only. because the theoretical yield you can calculate, but the actual yield is something you actually get. And the percent yield is just the actual yield divided by the theoretical yield times 100%. So they let you know how close you got to the percent yield. And there are a few times that your percent yield will actually be higher than your theoretical yield. Your actual yield might be higher. In that case, it's because you didn't purify the product good enough. I see this in the lab where you have water or other solvent still on the product, and then you get a falsely high amount of product. So there are some instances where there is also experimental error involved in the yields. So keep that in mind if you're actually doing this in a laboratory and not just studying it. So let's go on and talk about an example with this. We begin with 1.8 moles of titanium and 3.2 moles of chlorine. Use the following balance equation to find the limiting reactant and the theoretical yield. So there is a 1-to-1 molar ratio between moles of titanium and titanium chloride, and there's a 1-to-2 molar ratio between the titanium 4 chloride and chlorine. So the smallest determines the limiting reagent, and from that you can see it's the titanium. It's the chlorine because it gives the lowest amount. So you look at it for both and do the calculations. You can see, okay, so it's actually the chlorine that's the limiting reagent there. So we should get 1.6 moles of titanium 4 chloride. So for industrial processes, sometimes it's more costly for the reactant that is most difficult to remove from the product, and that's chosen to be the limiting reagent. So I mean, like say something that is a carcinogen, right? So in a case like, say you're using something really nasty like hexavalent chromium or something like that, you do not want to have excess hexavalent chromium because it is a carcinogen. So, and you wanna make sure that is all used. So it's not so. Also, sometimes it's economic. So certain reagents are cheap. So you want to be a little excess in those, not too much excess, but like to have a little excess of those to make sure that you get all the use of the other reagents. So like say for extracting metals from ores. Ores are typically expensive, but the carbon that is used to extract is typically not very expensive, or not as expensive as the ores. So typically you add in a little extra carbon just to make sure that you can get as much of the metal out of the ore as you can. Of course, using the laboratory, we use smaller amounts in grams, and so things are on a smaller scale. And in industrial processes, you can deal with thousands of tons. Also, to find limiting reagents and from our initial masses, sometimes we have to add a few steps to our calculations. So, give you an example here. You begin with 53.2 grams of sodium and 65.8 grams of chlorine. Find the limiting reagent and the theoretical yield from the balance equation. So sodium plus chlorine makes, it actually should be 2 moles of sodium. This is unbalanced. So 2 moles of sodium plus mole of chlorine makes 2 moles of sodium chloride. So, okay, it didn't write it on the equation, so it is correct. Okay, so solution map here, starting with a mole of sodium per, well, we have to start with the mass of sodium, then convert to moles of sodium, then do the ratio, and not listed the 2 in front, but it's 2 to 2, and then by the molecular weight of sodium chloride. Same idea with the chlorine, but the middle step is different. So middle step is different, and then the smallest amount determines limiting reagent. You can do it at moles. You can stop at moles if you want, a mole sodium chloride, or you can keep on going to mass. I like that they're going all the way to mass. So using this and putting in the missing spots, you can see that the chlorine is in fact the limiting reactant here. So now this was given, this has to be given. The actual yield is 86.4. So our theoretical yield is 108 grams and we're given 86.4 grams. That means that the percent yield is 86.4 divided by 108 times 100% or 80%. So hopefully this is all looking very straightforward. Students, like I said, usually find the middle steps, converting between reactants and products and the balanced chemical equation. That's the tough part for them. And also remembering the equations is sometimes hard for students. So here's another example. When 11.5 grams of copper oxide and 114.5 grams of carbon react, 87.4 grams of carbon are obtained by this equation. Determine the limiting reagent, theoretical yield, and percent yield. So starting with we're going to find the limiting reagent. So is this thing balanced? Yes, okay, good. It is in fact balanced. And this is actually the way that we would get copper. You would take copper ore, and so copper ore is something you dig from the ground, and then carbon is usually, we usually call it coke. It's a purified carbon, and then that reacts to form the metal that you want, and then carbon monoxide. And you typically do this in a blast furnace where you blast oxygen into the reaction vessel. So that's we refer to that as a blast furnace. So let's go ahead and do this then, and we'll see which one. Okay, so the other thing is, if I was a plant manager, and which one I would want to put the carbon in excess. So let's see if they actually balance this to have the carbon. Oh, good. So we start with the carbon and the ore, and it turns out we had a little extra carbon for the ore, and then the limiting reactant is the copper oxide. So and again, this is praise to the person that was designing this, because carbon's cheap. Carbon's cheap and ores are expensive, so it makes sense that you want to try and rip as much copper, and copper is a pretty valuable metal. It's not the most valuable, but it's pretty valuable, so you want to rip as much copper out as you can. And we find out the actual yield is 87.4 grams of copper. The amount of product, the theoretical yield, I'm sorry, the actual yield was 87.4 grams. The theoretical yield was 101.7 grams. And then doing the actual yield, we get 85.9%. You're like, wait a second, where is that, where is that coming from? Well, when you dig ore out of the ground, it's got other stuff in it. It's not purified carbon oxide. It's going to have other stuff in it. It's going to have calcium magnesium silicates, also known as slag. It's going to have maybe a little bit of dirt. It's going to have water. It's going to have other things. And they're just going to take the rocks and they're going to sell them as a supplier to the company. And right, I mean, and the company knows not everything in there is going to be copper. There might be other metals too. Maybe they find a little bit of platinum and gold. Hey, that's even better. But there's probably other metals in there like chromium or iron or something like that. So there'll probably be other things in there too. So it's the product might not even be pure. So that's one of the things when you're dealing with the real world. It's different than the chemistry class. So now that we've talked about reactants and products, let's talk about enthalpy. We haven't really talked about enthalpy too much. Well, we haven't talked about it at all. Enthalpy is the amount of energy that a chemical reaction can make under constant pressure. So, and it's a convenient thing, and like right now, and many times when you're in a chemical reaction, you're dealing with a constant pressure. So certainly right now, as I'm talking and chemical reaction taking place in my body, it's dealing with a constant pressure of about 1 atmosphere, because the atmosphere of the Earth, for instance. So delta H reaction works very well for circumstances like this. Sometimes the pressure is not the pressure is not constant, and then enthalpy can't be used. So there's other things to do then. But oh, and you might see this delta H reaction, RXN. That RXN means reaction. So that delta, that triangle before the H, and H is also enthalpy. So we say H, the term is enthalpy, and that triangle is the capital Greek letter delta, and it means change. It means, specifically final minus initial. That's what that capital delta means, the final minus the initial. Also, enthalpy H is known as a state function. So state functions have exact differentials, which means they are path independent. It doesn't matter how you get there. The values will always be the same. Internal energy is path independent. Gibbs free energy is path independent. Entropy is path independent, and Helmholtz free energy. These are terms used in other sections, other classes. Those are also path independent. It doesn't matter how you get there. Work and heat, though, these are path dependent. Those can change depending on what you do. But enthalpy will always be the same. You will get the same, if you burn a gallon of gasoline, you will get the same amount of energy from it no matter what. And enthalpy can also works proportionally, just like chemical reactions. When you burn a gallon of gasoline, you will get half the amount of energy if you burn a half a gallon. You'll get twice as much energy if you burn 2 gallons. So that's how an enthalpy works in a scalar way, based off of whatever base you're going on. So that's with the path independency. So chemical reaction, we covered this before. Exothermic means that the chemical reactions emit energy. And if it's endothermic, the chemical reactions absorb energy. And the sign, so if the delta H is positive means endothermic. If it's negative, it means exothermic. It has to do with the energy flow. Negative says it flows away from the system. Positive means it goes into the system. So that determines the direction of the flow. And this time, the system is the chemical reaction. So this shows it, the picture. So the y-axis on the paper screen going up is chemical potential energy, and the x-axis is just reaction coordinate. So starting with the reactants, and you go along with the products. If it's exothermic, the potential energy goes down, and then that difference energy is released. Opposite is true for endothermic reactions. So the reactants start at a low potential energy, and then the products are at a higher potential energy. That means the chemical reaction absorbs energy, and then the heat of reaction is positive, and it's endothermic, absorbs energy. So let's look at this equation here. Combustion of methane already balanced, and you're given the heat of reaction here being negative 802.3 kilojoules. And the K, that means 1,000. So it's 802,300 joules, known to 4 sig figs. So that's what this chemical reaction means. And it also, you have this, so it tells you it's exothermic, it's generating heat. And it also tells you relationships between these. So for every 1 mole of methane, it's going to evolve 802.3 kilojoules of heat. Same thing for every 2 moles of oxygen reacted, 1 mole of carbon dioxide formed, and 2 moles of water formed. So these can also be referred to, if you get a chemical reaction and there's none of those have a unity in terms of the number, you can use the units moles reaction. So this delta H does contain the units energy per mole reaction. So the mole is an implied term there. So here's an endothermic reaction. Nitrogen plus oxygen forms 2 nitrogen monoxide. The heat of reaction here is positive 182.6 kilojoules. So this tells us that that energy is absorbed in a system. And the same thing in the system being the chemical reaction. Same rules apply, the same molar ratios in the mole of reaction. This is all the same thing as before with the exothermic reactions. So delta H also goes in stoichiometry, and it has to deal with the same ratios. It's as if the energy, the enthalpy of the reaction, is a product, and it is in per moles reaction, and it says, and I've said this before, as written. It's got the units per mole reaction. So let's look at an example of this. We have this chemical reaction here. Propane plus 5 oxygens yields 3 carbon dioxides and 4 waters. The heat of reaction here is negative 2044 kilojoules. When 1 mole of propane reacts with 5 moles of oxygen to form 3 moles of CO2 and 4 moles of water, 2044 kilojoules of heat are emitted. So that's kind of what this equation means. And you can use these ratios as conversion factors. So let's figure out the solution map. What is it asking for? That's okay. We're not given a number to go yet. Okay, oh, here we go. So we're burning something. We're burning, so 11.8 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So how much energy are we going to get from burning 11.8 kilograms of propane? So we're going to start with, the idea is we're starting with mass of propane, we're going to moles of propane, and then moles of propane, we can go to the heat of the reaction, and then we can stop right there. So this is going to be a pretty easy problem. So start off with the 1.18 times 10 to the 4 grams of propane, moles of propane, and you can again calculate out the moles of propane using the periodic table and previous knowledge. And then from the balanced chemical equation, we get the amount of heat per mole of propane. And from this, we get 5.47 times 10 to the 5th kilojoules, and we have a negative sign there. Negative means exothermic, and that's the heat emitted. So the energy change is negative, meaning exothermic of 5.47. What is it? 547,000 kilojoules. So a lot of energy. That's quite a bit of energy. So it's amazing how much energy is in fuel. I'm always surprised when I see this. You could argue when you say the total heat emitted, then whether or not the negative sign is implied. I would keep the negative sign in, and then depending on what you do the calculation, because the negative sign certainly shows you the energy flow. So review, and this is a tough chapter. A lot of students have a hard. This is when chemistry can start to become difficult, and like I said, especially when you deal with the middle steps, when you have to determine in a balanced chemical equation where to get the ratios. So when you do this chemical accounting, this is called stoichiometry. We talked a little bit about limiting reagent theoretical yield and percent yield. Students tend to have the hardest time with the theoretical yield and trying to determine which one is the which is the least, the smallest one should give the theoretical yield. A lot of times, some of those mistakes are the chemical equation is not balanced correctly. So make sure that you balance chemical equation correctly. So I'm using my teacher years to tell you where you can get this. Percent yield, usually don't see too much issues with that. So we've talked about these, and the enthalpy. Enthalpy, it's usually easier to deal with because there's fewer intermittent steps. So it's kind of, you can go right, you can get to the answer a lot quicker. So students tend to like these a little bit more. But you can look at the enthalpy, the heat of reaction associated, and stoichiometry follows the heat of reaction as well. But this makes sense though, right? Because if I have a kilogram of gasoline and I burn it, I assume I can get twice as much energy if I burn 2 kilograms and 3 times as much if I burn 3 times as much. So this kind of makes sense, right? So this would make sense that the enthalpy of a reaction follows the same idea as stoichiometry. Here are the learning objectives and legal, and thank you again for listening.